The assessment of the universe's commencement and its ceaseless development is currently at a critical stage, with cosmology defying a portion of its most fundamental vulnerabilities. A key center is deciding the rate at which the universe is extending. For over 10 years, two significant methodologies for estimating this extension have delivered disconnected results. Ongoing perceptions of the current situation with the universe demonstrate that the pace of development, known as the Hubble constant, is around 9% higher than forecasts derived from information from the early universe. Researchers had trusted that the James Webb Space Telescope, JWST, the most exceptional telescope at any point made, would provide a conclusive answer for this issue. However, the new, notable information from JWST has simply extended the inconsistency, prompting inquiries about the legitimacy of the established cosmological model. This has ignited intense discussions within mainstream scientists about whether new physics are needed to change or totally supplant the current hypotheses that have held for over 40 years. This possibility is both exciting and disrupting, as it suggests that we may be neglecting a fundamental part of the universe that could decisively alter how we might interpret its beginnings. The starting points of the universe trace back to the Big Bang, a gigantic blast that, in an instant, created energy, matter, and space. From this, the universe began as a very hot and dense plasma, a combination of matter and antimatter particles. These particles impacted and destroyed one another, but researchers believe a subtle imbalance allowed slightly more matter than antimatter to form, preventing the universe from obliterating itself. Gravity then consolidated the plasma, heating it to the point where sound waves, known as baryon-acoustic oscillations, propagated through it at speeds greater than a fraction of the speed of light. Meanwhile, the dense energy content of the early universe stretched spacetime itself, pushing matter far enough from the extreme heat to survive. As the universe expanded like an inflating balloon, ordinary matter is thought to have begun clumping together around invisible dark matter, eventually forming the first galaxies. These galaxies are believed to be interconnected by a vast cosmic web, linked through dark matter and energy. As the universe continued to grow, both the energy density and the pace of expansion gradually decreased. However, around 5 billion years ago, galaxies began to retreat from one another at an accelerated speed, driven by a mysterious force referred to as dark energy. The most widely accepted theory for dark energy is that it acts as a constant force woven into spacetime itself, embedded in the fabric of the universe's development. This force, known as lambda in Einstein's theory of general relativity, maintains a constant density as the universe grows, while the density of normal matter declines over time. Eventually, dark energy became the dominant force driving the expansion of the universe, alongside dark matter and ordinary matter. Together, these forces form the lambda-cold dark matter, lambda CDM model, which describes the universe's development and predicts its eventual fate, known as heat death or the Big Freeze. While many of the model's predictions have been confirmed, the nature of dark energy and dark matter remains unresolved. One of the main challenges facing cosmologists is the Hubble tension. Depending on the method used, measurements of the universe's expansion rate yield conflicting results. This discrepancy is so pronounced that it has become one of the field's most pressing issues. Observations from the early universe suggest a higher rate of expansion than the lambda CDM model predicts. These early measurements have been rigorously tested and validated through various observations. According to Nobel laureate astrophysicist Adam Rees, who led the team responsible for the latest JWST measurements, the only plausible explanation for the discrepancy is that our current model is missing something crucial. Measuring the expansion rate of the universe requires more than just a simple observation. One of the primary methods involves studying the cosmic microwave background, CMB, which represents the universe's first light, emitted approximately 380,000 years after the Big Bang. This imprint is visible across the entire sky and has been mapped extensively, most notably between 2009 and 2013, when the European Space Agency's Planck satellite provided a detailed map of the CMB. This map shows the universe as nearly uniform, with slight temperature variations marking regions of sequential matter density. These variations reflect the imprint left by baryon-acoustic oscillations, which helped cosmologists calculate the Hubble constant, yielding an estimate of roughly 67 km per second per megaparsec. To explain this, a galaxy 1 megaparsec away would recede at 67 kilometers per second, while a galaxy 20 megaparsecs away would retreat at 1,340 kilometers per second. If a galaxy were farther than 4,175 megaparsecs away, it would recede faster than the speed of light. Another method for determining the expansion rate involves studying Cepheid variables, stars whose outer layers expand and contract in a regular pattern as they absorb and emit radiation. Discovered by astronomer Henrietta Swan Leavitt in 1912, this behavior allows astronomers to measure the star's absolute brightness, which can then be used to estimate their distances. The Cepheid variable method, part of what is known as the cosmic distance ladder, has been a crucial tool for measuring vast distances across the universe. The first step of this ladder involves measuring nearby Cepheids and determining their distances. From there, astronomers can measure more distant stars and supernovae by observing their redshift, and compare these measurements to calculate the Hubble constant. In 2019, Rees and his team used this method to study the Milky Way's nearest neighbor, the Large Magellanic Cloud. Their results were striking, showing a substantially higher expansion rate of 74 kilometers per second per megaparsec compared to the Planck data. While the Hubble Space Telescope made significant contributions, its accuracy was limited in crowded regions of space, causing distant Cepheids to blend with neighboring stars. Some cosmologists have suggested that the discrepancy could be due to measurement errors. However, when the James Webb Space Telescope was launched in December 2021, expectations were high that it could either resolve or confirm the discrepancy with its 6.5-meter-wide mirror, nearly 3 times the size of Hubble's, and superior infrared capabilities. JWST could observe fainter objects and detect a broader range of wavelengths. Studies examining Cepheids in the galaxy NGC 4258 to supernova explosions revealed results almost identical to Rees's previous findings, with an expansion rate of about 73 kilometers per second per megaparsec. Other measurements, including those by Wendy Friedman using the Hubble Space Telescope and gravitational lensing, returned similar values of 69.6 kilometers per second, 66.6 kilometers per second per megaparsec, respectively. Discoveries have created a ruckus in the cosmological community, as verified by cosmologist Ronan Kai from the University of California. Even a little disparity of only 7 kilometers per second is extremely unlikely to be an irregular mistake, especially considering the accuracy of the measurements. This has prompted a division among cosmologists, with some suggesting measurement errors, while others propose the need for new physics or a combination of both. Kai believes a significant part of the data points toward the need for new physics. One leading theory is that dark energy's behavior may have evolved over time. If dark energy was once stronger and has progressively weakened, it might have caused the universe to appear smaller in its early stages, leading to a faster expansion rate. Other hypotheses propose the presence of 2 kinds of dark energy or interactions between dark matter and light, but these ideas come with complications that many cosmologists are reluctant to accept without more evidence. The discoveries made by the James Webb Space Telescope, JWST, are not just testing how we might understand dark energy and dark matter, but are also reshaping our perspectives on galaxy formation. By observing galaxies farther back in time than ever before, JWST has uncovered galaxies that are much more massive and developed than anticipated, forming just 300 million years after the Big Bang. These early galaxies, which were thought to mostly consist of young, hot stars, were found to contain heavy elements and, surprisingly, very massive black holes at their centers. These findings challenged the conventional model of galaxy evolution, suggesting that the processes of galaxy formation might have been faster and more efficient than previously thought. Moreover, these discoveries deepen the mystery of dark matter and dark energy, both of which remain poorly understood despite being dominant components of the universe. Dark matter, which interacts only gravitationally, continues to evade direct detection, prompting ongoing investigation. Similarly, dark energy, responsible for accelerating the universe's expansion, presents puzzles like the Hubble tension, raising the possibility that its properties may not be constant across spacetime. Alternative theories propose dynamic forms of dark energy that could evolve over time, influencing the expansion rate at different stages of the universe's history. To address these mysteries, astronomers will need both advanced observational tools, like the James Webb Space Telescope, and theoretical frameworks capable of incorporating new data without discarding the successes of current models. The implications of JWST's discoveries extend far beyond cosmology, touching on broader astrophysical questions, including the origins of life and the conditions necessary for life on other planets. By studying distant galaxies, astronomers hope to uncover clues about how Earth-like planets could form around other stars, offering insights into the prevalence and diversity of life across the universe. Looking forward, the James Webb Space Telescope promises to push the boundaries of our understanding of the universe. Its extraordinary sensitivity and resolution will allow cosmologists to study the atmospheres of exoplanets, map galaxies more meticulously, and examine the earliest moments of cosmic history with unmatched precision. JWST's ongoing mission is set to continue transforming our understanding of physics, astronomy, and our place in the universe. Whether uncovering the secrets of dark matter and dark energy, unraveling galaxy evolution, or searching for life beyond Earth, the telescope is poised to change our view of the universe in ways once thought impossible. In short, the intersection of cutting-edge technology, theoretical development, and precise observation heralds a new era for cosmology and astronomy. JWST's contributions will refine our understanding of the universe's beginnings, challenge established theories, and open doors to monumental discoveries. As we continue our journey of exploration, the universe's secrets await, and with JWST at the forefront, we are poised to unveil the mysteries of our vast legacy and future. The James Webb Space Telescope offers more than just precise measurements of the universe's expansion and detailed observations of early galaxies. It is set to tackle some of cosmology's deepest questions. While the possibility that our understanding of the universe could be fundamentally flawed is not new, JWST's accuracy has sharpened this potential. Key to the universe's structure are dark matter and dark energy, which remain poorly understood. JWST's ability to focus on the early universe and observe galaxies that formed only 300 million years after the Big Bang has provided rare insights into galaxy formation. These observations challenge the established hypothesis that galaxies should have taken longer to form, suggesting that processes like star formation and black hole development may have been more efficient in the early universe. Additionally, JWST observations are helping to advance the study of dark matter, a mysterious substance believed to have played a crucial role in shaping the universe's structure through its gravitational effects. JWST's precision may help clarify how dark matter influenced galaxy formation, and perhaps reveal new properties of this elusive substance. Beyond dark matter, JWST is also aiding the study of exoplanets and the conditions that could allow life to flourish on other worlds. One of the telescope's primary objectives is to analyze exoplanet atmospheres, searching for signs of habitability or even life. By studying the chemical composition of these atmospheres, scientists hope to determine the conditions that might support life elsewhere in the universe. This could offer insights into how common Earth-like conditions might be. As JWST continues to analyze data, it becomes increasingly evident that we are on the brink of uncovering new physics. Whether unraveling the nature of dark energy, investigating the unexpected complexity of early galaxies, or examining the behavior of dark matter, JWST is opening new avenues for understanding the universe. The telescope is not simply refining our current theories, it is challenging them, encouraging scientists to rethink fundamental assumptions and explore new possibilities. These discoveries are pushing the boundaries of physics, space science, and even philosophy. As we evolve our understanding of the laws that govern our existence, we are not just learning about distant stars and galaxies, we are gaining profound insights into the very nature of the universe. The questions raised by JWST's discoveries could lead to a paradigm shift in how we understand the origin, structure, and fate of the universe. As we continue to explore the universe from the perspective of the James Webb Space Telescope, the potential for a paradigm shift in how we understand the universe becomes increasingly likely. The telescope's remarkable capabilities have already provided a wealth of data that challenges many of our long-held assumptions about the universe. For example, the observation of early massive galaxies forming just 300 million years after the Big Bang raises important questions about the timescales and processes involved in galaxy formation. These galaxies appear much more mature than expected, suggesting that certain processes, such as star formation and black hole development, may have occurred much more rapidly and efficiently than we had previously imagined. This discovery has sparked intense debate among cosmologists about whether our current models for galaxy formation and cosmic structure need to be revised. Moreover, JWST's study of the early universe has revealed further complexities in the interaction between matter, and dark energy. The telescope's infrared capabilities allow it to peer deeper into the universe, examining objects and events that occurred in the first few 100 million years after the Big Bang, a time previously beyond our observational reach. These observations are crucial for understanding the role of dark matter, which makes up around 25% of the universe's mass but remains one of the most elusive aspects of the cosmos. While dark matter does not emit light and can only be detected through its gravitational effects, JWST's precision may help clarify how dark matter contributed to the formation of galaxies and large-scale cosmic structures. This is an essential step toward understanding how our universe came into being and how it continues to evolve. In addition to the ongoing quest to understand the fundamental components of the universe, dark matter, dark energy, and galaxy formation, JWST observations are also offering exciting new possibilities in the search for life beyond Earth. One of the telescope's key missions is to study the atmospheres of exoplanets, searching for signs of habitability. By investigating the chemical composition of these exoplanet atmospheres, scientists hope to identify the presence of molecules such as oxygen, methane, and carbon dioxide, which could be indicators of life. JWST's ability to observe exoplanets in greater detail and with higher sensitivity than ever before could bring us closer to answering the crucial question: are we alone in the universe? JWST's contribution to this field goes beyond identifying potentially habitable exoplanets. It also promises to help us understand the environmental conditions that could support life. This includes studying the climate and atmospheric conditions of distant planets and understanding how these factors could influence the potential for life to arise. By examining the chemical interactions within these exoplanetary atmospheres, scientists hope to uncover new insights into the processes that govern planetary habitability, insights that could have profound implications for the search for life beyond Earth.